In this video, I'll be explaining the abstract definition of the covariant derivative. If you're just joining this series now, you'll probably want to watch videos 17, 18, and 19 first, so you can understand the easier definitions of the covariant derivative first. The link to those videos are in the description. So the abstract definition of the covariant derivative is the last definition I'm going to cover, and it's going to be the hardest one because it's mostly just pure algebra. Also, in this video, I might use any one of these three symbols to represent basis vectors. This one here is new, but it's the same thing as the other two. It's just a partial derivative in the direction of the kth coordinate. So when it comes to the abstract definition of the covariant derivative, there are basically two main reasons why we'd want to study it. The first reason is that using the abstract definition, we're going to find that there are actually several different covariant derivatives, not just one. So the abstract definition of the covariant derivative is more general than what we were using before. However, there's still going to be one main version of the covariant derivative that we care about, and that is called the Levi-Civita connection, which comes from the fundamental theorem of Riemannian geometry. The second reason for using the abstract definition is that it allows us to extend covariant derivatives to all tensor fields, and that includes scalar fields, vector fields, covector fields, metric tensor fields, as well as all other tensor fields. And to help you understand how we invent the abstract definition of the covariant derivative, I'd like to talk about how we invented the idea of vector spaces, because vector spaces are a somewhat abstract idea as well. So you're probably familiar with R2, which is the set of pairs of real numbers. And the members of the set R2 serve as an inspiration for vector spaces. So let's look at some properties of the elements of R2. So this might be pretty obvious, but we find that there's a reasonable way to add two elements of R2 together, right? We just add the top numbers together and add the bottom numbers together, and we get a new member of R2. So this property shows that given two members of R2, we can define their sum, which is also a member of R2. Similarly, there's also a reasonable way to scale elements in R2. We just multiply the top and bottom numbers by the scalar, and we get a new element in R2. So given an element v in R2 and a scalar real number, the scaled version of v is also in R2. Another property is that we can add elements of R2 either frontwards or backwards, and we end up with the same result, so the order of addition doesn't matter. We also find there's a special zero element in R2, where if we add a vector with the zero element, we get back the same vector, so that's another property. Also, we find each element has a negative version of itself, where if we add the positive version and the negative version together, we get the zero element. So if we keep going, we can gather together a whole bunch of properties that the members of R2 follow. We get some addition properties, some scalar multiplication properties, and some properties for distributing multiplication over addition. Now, given this, mathematicians basically took all these properties and turned them into a definition, and that's the definition of a vector space. A vector space is a set of vectors and a set of scalars, along with rules for addition and scaling that follow all of these laws. So we started with the properties of R2 and used those to define a vector space, which is a more abstract idea. So a vector space is sort of like a generalized version of R2. But given this new definition of a vector space, we can find other examples of things in mathematics that obey the same vector space laws. For example, the set Rn is a vector space. Also, the set of polynomials in the x variable form a vector space, and the set of partial derivatives of coordinate variables also form a vector space. Right? We can add and scale all of these things in a way that makes sense and get linear combinations. So the advantage of inventing the abstract idea of a vector space is so that we can take a lot of things that seem different on the surface, but on a deeper level, they behave in a way that's similar. And we can use the framework of vector spaces to understand all these different ideas in math. Now, inventing the abstract definition of the covariant derivative follows a similar process. We start with the definition of the covariant derivative that we're familiar with and look at some of its properties, and then use those properties to create a new abstract definition. And using that abstract definition, we can define many other types of covariant derivatives as well. So let's take a look at a few properties of this covariant derivative that we're used to so we can invent the abstract definition. And just as a reminder, the intrinsic covariant derivative that we're used to from the previous video just takes the derivative of a vector field in a given direction. And after using product rule and defining the Christoffel symbols, we end up with this expression. So let's say we have the covariant derivative of this vector in a direction given by this linear combination. And to save space, I'm actually going to change the partial derivative notation to this. So remember, these are just partial derivative operators. So we just apply the derivative in this direction and then distribute, and then we can change these partial derivatives back into covariant derivatives, and we get this. So we basically just showed that the covariant derivative is linear for the direction vector input. We can either add and scale the direction vectors before taking the covariant derivative, or we can add and scale the results after taking the covariant derivative. So that gives us this property here. We can also take the covariant derivative of a sum of vectors, and turning this into a partial derivative, we get this. And so we can distribute it to both vectors, and then switch back to the covariant derivatives. So this shows that the covariant derivative is additive for the vector field part. We can either add before taking the covariant derivative or add after, and we get the same result. Now, if we take the covariant derivative of a vector field scaled by a scalar, we can change this to a partial derivative and then use product rule, so we get one term with the derivative of the scalar and one term with the derivative of the vector. And then turning these back into covariant derivatives, we see that the covariant derivative basically obeys a kind of product rule, sometimes called the Leibniz rule. Also, taking the covariant derivative of a scalar function is the same thing as taking the directional derivative of that scalar function. So this tells us how to compute the scalar derivative in the product rule here. And this is actually why we write the covariant derivative using the same notation as the directional derivative. The covariant derivative is basically like a generalization of the directional derivative for scalar fields that also works for vector fields. So we're going to take these four properties and start using them as a new definition for the abstract covariant derivative. So a covariant derivative is an operator with two input slots. It takes a direction vector, and then it takes an input field. And then the output would be the rate of change of that field, which would be a new field. And sometimes this covariant derivative operator is also called a connection. And I'll take a couple minutes to explain where the name connection comes from. So let's say I have a spherical surface, which I'm calling S. Now, from previous videos, you should already be familiar with the idea of parallel transporting a vector along a curve, as you can see here. And parallel transport is given by the condition of the covariant derivative of the vector field being 0. Now, what parallel transport is doing is it's connecting the tangent vector space at the red point P to the tangent vector space at the blue point Q. So in the tangent vector space at point P, which we call TPS, the vector points in this direction. And after parallel transporting it along this curve, in the tangent vector space at point Q, which we call TQS, the vector points in this direction. So this is what I mean when I say parallel transport connects vector spaces. It gives us instructions for turning a vector in the tangent space TPS into a vector in another tangent space, TQS. So parallel transport gives us a way to map vectors from TPS to TQS. And since parallel transport is defined using the covariant derivative, it's really the covariant derivative that's providing the connection between the tangent spaces in this curved space. So that's why a covariant derivative is sometimes called a connection, because we can use it to connect different tangent spaces at different points in the curved space. Now, you might recall from previous videos that we defined the Christoffel symbols like this, where we expand the partial derivative of the basis vectors out as linear combinations. And the abstract version of this using the covariant derivative would be this. And when we're talking more abstractly, these Christoffel symbols are also sometimes called connection coefficients. Now, it turns out that given the information we have now, we don't actually have enough information to solve for a unique set of Christoffel symbols. And that's why I said at the beginning of the video that there are many possible covariant derivatives. That's because there are many possible ways to define these connection coefficients. But there is a way that we can get a unique solution for the Christoffel symbols, and that's by introducing two new properties called the torsion-free property and the metric compatibility property. And I should probably mention that although I've defined the torsion-free property like this, a lot of textbooks will use this more advanced definition, where this symbol here is the Lie bracket of vectors. And the Lie bracket basically just tests for the difference between the vectors when we apply them in opposite orders. Now in our case where the vectors are partial derivative operators, since partial differentiation works the same in both directions, the result of the Lie bracket ends up being 0 anyway. So with a 0 Lie bracket, we can use this simplified version of the torsion-free property. There are more advanced situations where the Lie bracket is non-zero, but I'm not going to cover those in this video. So the torsion-free property says that the covariant derivative of Ej in the Ei direction is the same thing as the covariant derivative of Ei in the Ej direction. It's sort of inspired by this rule with traditional derivatives where the order of partial differentiation doesn't matter. So given the Christoffel symbol expansion of these two derivatives, since these two covariant derivatives are equal, we're forced to conclude that these two sets of Christoffel symbols are equal. So the torsion-free property means that we're free to swap the lower indexes of the Christoffel symbols without changing their value. The second property is the metric compatibility property. And this is sort of a special version of the product rule that's applied to the dot product. So the result of this derivative of this dot product is a sum, where in the first term, the first factor is differentiated, and in the second term, the second factor is differentiated. So this might seem like a really abstract rule, but what this property is really saying in plain English is that when we parallel transport two vectors, their dot product will stay the same. So remember, the condition for parallel transport of a vector is that the covariant derivative of the vector is 0. So these formulas would mean we're parallel transporting the vectors v and u along a curve. So if we take this metric compatibility property and these parallel transport conditions, this means that this goes to 0 and this goes to 0. So the entire right-hand side here goes to 0. And that means that the covariant derivative of the dot product is 0. Or in other words, the dot product stays constant. And remember, since the result of a dot product is just a scalar, the covariant derivative of the scalar is just the partial derivative of that scalar. That was one of the 4 properties of the covariant derivative we stated earlier. So if we were to visualize this, if we start with these two vectors v and u and start parallel transporting them along the curve, the angle between these two vectors would stay constant because the rate of change of their dot product is 0. And of course, since the vector v's squared length is just v dot v, the metric compatibility property also means that the vector will have constant length when it's parallel transported along a curve. Now, one consequence of the metric compatibility property can be obtained if we replace these vectors with the basis vectors ei, ej, and ek. And of course, we can replace these covariant derivatives with the Christoffel symbol expansions. And again, we can replace this covariant derivative with a partial derivative since the dot product is a scalar. Now, bringing the Christoffel symbols out in front, we can convert all these basis vector dot products into metric tensor components, so we get this result. Now, I'd like you to notice what happens when we use the torsion-free property and the metric compatibility property together. Using metric compatibility, we can write out these 3 equations, And these are all basically the same equation, just with the I, j, and k indexes switched around. And let's say we want to compute this expression right here. It's just these two derivatives added together with this one subtracted. So I'm going to color code these terms here. Notice how the blue terms are the same because the torsion-free property lets us swap the lower indexes of the Christoffel symbols. And by the same reasoning, the red terms are both equal and the green terms are both equal. So since this third derivative is negative, I'm going to write negative signs in front of this third equation. And adding all these together, we see that the blue terms cancel, the green terms cancel, and the red terms add together. So this expression is just equal to twice the red term. And if we sum on both sides with the inverse metric tensor, we get this equation where we've solved for the Christoffel symbols. So using the torsion-free property and the metric compatibility property together, we are able to solve for the Christoffel symbols. And that means we found one particular version of a covariant derivative. And the covariant derivative that uses these Christoffel symbols is called the Levi-Civita connection. And this is basically the result stated by the fundamental theorem of Riemannian geometry. And when we're talking about Riemannian geometry, a Riemannian manifold is basically just a curved space where we have a metric for measuring distances. Anyway, this theorem states that there is a unique connection, or a unique covariant derivative, that is torsion-free and has the metric compatibility property. And again, this unique connection is called the Levi-Civita connection, and it's the connection where the Christoffel symbols, which are sometimes called connection coefficients, are given by this equation. So I've basically spent 3.5 videos describing the Levi-Civita connection, which is the covariant derivative we're all familiar with. But at the beginning of this video, I told you that there are other covariant derivatives as well. So let's take a look at an example of another covariant derivative. So this will be a covariant derivative where all the Christoffel symbols are 0, and I'm going to call this the boring connection. So just to remind you from the previous videos, we derived these Christoffel symbols for the sphere, and these were the Christoffel symbols for the Levi-Civita connection. And when we use this covariant derivative to perform parallel transport of this vector along the curve, we ended up with this vector field, where the vector ends up sort of spinning relative to the basis vectors. And this spinning behavior is because the general solution for the vector components during parallel transport along this curve involved sine and cosine with an angular frequency. And the angular frequency depends on the latitude of the curve. So that's parallel transport with the Levi-Civita connection. Now, if we try the boring connection, where all the Christoffel symbols are 0, we'd get a different covariant derivative, where all these terms go to 0. And the parallel transport equations end up being much simpler, just setting these partial derivatives to 0. So the solutions for the vector field components are just constants. So parallel transporting this vector results in the vector always facing the southward direction. So the Levi-Civita connection and boring connection are both covariant derivatives, since they both satisfy these 4 properties. But when we look at the metric tensor for the sphere, only the Levi-Civita connection satisfies the metric compatibility condition. The boring connection always has the right-hand side of this equation equal to 0, and the derivative of this component is not always equal to 0. So the boring connection is not metric compatible. And both the Levi-Civita connection and boring connection can be used to perform parallel transport, but the results of the parallel transport are different, and they end up connecting the tangent spaces on the sphere in different ways. And we can define all sorts of other connections, but most of the time, the Levi-Civita connection is going to be the one that's most important to us. So hopefully you see why there are many possible different covariant derivatives. Now let's move on to extending covariant derivatives to all tensor fields. Let's start by defining covariant derivatives for covector fields. So way back in my Tensors for Beginners video number 4, I introduced the epsilon basis covectors, which are defined by this equation here. So when the covector epsilon j acts on the basis vector ei, we get the Kronecker delta ji. And these epsilon covectors act as a basis, so we can write any covector as a linear combination of these epsilon covectors. And in the tensor calculus video number 6, I talked about how, just as this partial derivative is the calculus equivalent of the basis vector EI, this differential duj is the calculus version of the covector epsilon j. So if we take the covariant derivative of a covector alpha, we can expand alpha as a linear combination of the epsilon basis covectors. And then we can use the covariant derivative version of the product rule, or the Leibniz rule. Now, the covariant derivative of a scalar is just the partial derivative, and we can expand the covariant derivative of the basis covectors using this formula here, where these lambda coefficients play a similar role as the Christoffel symbols, but for covectors instead. And changing these j indexes to k, we get this formula. Now, it turns out we don't need to put any more work in to solve for these lambda coefficients. We actually already know what they are. And to show that, I'm going to examine the covariant derivative of a covector alpha acting on a vector v. Now, it's a known fact that every covector can be written as a vector and a dot product, with the right side of the dot product left empty. So in the case of the alpha covector, we're going to say that the alpha covector is equal to a dot something. And so we can write alpha of v as a dot v instead. And we can again use the metric compatibility property to expand this out using a product rule. And now I'm going to convert these a dot somethings back into alphas. Next, we're going to expand everything. So we can expand the covector alpha with the epsilon basis and expand the vector v with the e basis. And we can expand this covariant derivative of the covector alpha using the formula we derived on the previous slide. And we can expand the covariant derivative of the vector v using our normal well-known formula. So now I'm going to take the VR components outside, since covectors are linear, and we can scale either the inputs or the outputs. And I'm going to take this term outside the covector as well. So epsilon k of ER is the Kronecker delta KR. So we can cancel out the R indexes and get k here. And epsilon k of V is just the component VK by definition. And alpha of EK is the component alpha k by definition. And expanding all this out, we get this. Now notice that this derivative of a product can be expanded using product rule. And the product rule would give us exactly what we see on the right side of the equation here. So because this and this are equal, we can just cancel them from either side of the equation. And looking at this, I'm just going to relabel some of the indexes here. So I'm going to switch the j and k indexes around, and that gives us this. And we can divide both sides by the alpha and v components to get rid of them. So what we found here is that the lambda coefficients are really just the negative of the Christoffel symbols. So the covariant derivative of a covector field has basically the same formula as the covariant derivative of a vector field, except we just have a negative sign here. Now, in addition to vectors and covectors, we can also define the covariant derivative of a general tensor field if we just declare this property here to be true, where the covariant derivative of a tensor product can be expanded out using another version of the product rule, where we get a sum of tensor products, where the first term has the first factor differentiated, and the second term has the second factor differentiated. So this would let us take the covariant derivative of the metric tensor, because the metric tensor can be written as a linear combination of covector-covector tensor products. So starting with this, we can use the product rule once to get two terms, where we differentiate the components in the first term and differentiate the tensor product in the second term. Now we can use this property to differentiate the tensor product and get another two terms. So you'll notice that we can write the covariant derivative of these covector basis vectors, which we said earlier we could expand out using the lambda coefficients, which are equal to the negative of the Christoffel symbols. So making these substitutions gives us this. So given this formula, we're going to try and write all these tensor products of covectors using these same indexes. So we're going to switch the R and K indexes here, and we're going to switch the S and K indexes here. And now we can factor out this tensor product of basis covectors to get this. So you'll notice that the covariant derivative of the metric tensor has two negative Christoffel symbol terms. So there's a pattern going on here. Vectors are 1, 0 tensors because they obey 1 contravariant transformation rule and 0 covariant transformation rules. So they get 1 positive Christoffel symbol term. And covectors are 0, 1 tensors because they obey 0 contravariant transformation rules and 1 covariant rule. So they get 1 negative Christoffel symbol term. And the metric tensor is a 0, 2 tensor that obeys 2 covariant transformation rules, so it gets 2 negative Christoffel symbol terms. So basically, the covariant derivative of an mn tensor will give us m positive Christoffel terms and n negative Christoffel terms. Basically, the covariant derivative gives us a derivative term for the components and 1 extra term for every basis vector or covector that we have. So using this rule, we can determine the covariant derivative of any arbitrary tensor. Also, if we recall the metric compatibility property, we can see that this partial derivative is equal to this. And so all of this actually cancels out to 0. So it turns out that the metric compatibility property means that the covariant derivative of the metric tensor in any direction is always going to be 0. Another way of writing this is as follows, where we just leave out the direction vector of the covariant derivative because the covariant derivative of the metric tensor is 0 in every direction. And if you recall the Christoffel symbols that we derived for the sphere, if we compute the covariant derivative of the metric tensor, we do indeed find that the result is equal to 0. And that's true for all curved spaces as long as the metric compatibility property is true. So we've learned a lot in this video, but to summarize everything, the abstract covariant derivative is defined using these 4 properties here. And we can expand the covariant derivative using the Christoffel symbols. Also remember, a covariant derivative provides a connection between the tangent spaces in a curved space, and it does this by providing a definition of parallel transport, which means that the covariant derivative of a tensor is equal to 0. And we introduced the torsion-free and metric compatibility properties, and remember, metric compatibility, if we're speaking in plain English, it just means that parallel transport keeps the dot product of vectors constant as they are being parallel transported. So given these parallel transport conditions, the rate of change of the dot product is 0. And using the torsion-free and metric compatibility properties, we can derive a unique set of Christoffel symbols, which define a unique covariant derivative called the Levi-Civita connection. And this fact is called the fundamental theorem of Riemannian geometry. And remember, while the Levi-Civita connection is very important, it's not the only covariant derivative. We can easily define another covariant derivative just by picking different Christoffel symbols. And different covariant derivatives will result in different instructions for parallel transport. And in total, we've shown the covariant derivative of a scalar field, a vector field, a covector field, and a metric tensor field. And we can use this property to get the covariant derivative of any general tensor field. Anyway, this finishes my discussion of the covariant derivative. I hope you found these videos helpful.